Hey, my name is Austin Rowland, and this is Physics 2212 Lab 3, which was about the magnetic field of a bar magnet. So, introduction for this lab. The purpose of this lab was for us to calculate the magnetic field values at different distances and directions from a bar magnet to understand the relation between distance and magnetic fields. And the results that we had, quick overview from this experiment, was that n was equal to 2.56 and the magnetic dipole moment was equal to 4.59 area times meters squared. So the experimental procedure that we used for this was to one, align our phone to account for magnetic north. Use a magnetic field measuring app with the magnemeter in your phone to find the magnetic field on and off axis. Third step was to derive constants for the equation of a magnetic field produced by a bar magnet. And four was to produce a model of the bar magnet's magnetic field and find the magnitude at the same distance and the off axis location using a Glowscript computer model for that. So, fundamental principles in this experiment are listed below. So, here we have the equation for magnetic field. Here's the magnitude of bar magnet's magnetic field related to something that we haven't quite seen before. And then here is the natural log plot of how those are all related to one another. So distance dependence for the bar magnet can be expressed as followed. So that second equation on the last slide that we saw there. To find this value for n, we measured the magnitude at various distances. And to ensure our accuracy for this experiment, we took 3 trials for each distance. And this is what our experimental data looks like through this. So here we can see for each distance, we took 3 trials for the distance and the magnitude of that magnetic field. Down here, we have the averages, and then they eventually are plotted through these points at the bottom on here. And here we see that we get this line of best fit equation for y equals negative 2.56 minus 13.9. So, experimental observation. So, as the phone moves closer to the bar magnet, the measured x component of the bar magnet's magnetic field increases. And as we move the phone farther away from the magnet, the x component of the bar magnet's magnetic field measures near zero. Calculations. So, using that second equation from our fundamental principles slide, we can make a logarithmic plot of this equation to obtain a plot with a straight slope and y-intercept. So here we found from our experimental data that the slope was negative 2.56 and that the y-intercept was negative 13.9. And we can use these to calculate our magnetic dipole moment, which will be used in the computer model. And here are those calculations as shown to the right. Here is some of the screenshots from the Glowscript computer model. So the function for creating that magnetic field over here on the top left, all of our different calculations for different observation locations for magnetic fields on axis and on perpendicular axes to the bar magnet are on the right over here. And then on the bottom left, we have the code to visualize the magnetic field 45 degrees off axis. And here's what that visualization looks like. So the lab 2 results, here we can see these B values were printed. So the two ones that were on axis are seemingly twice as large and in opposite direction as all of the perpendicular magnetic fields. And then we have our calculated value for D that we found using the D perp values from our experimentation. And then we have finally the B measurement for 45 degrees off axis at distance D down here below. And just so that we can kind of compare, we have that B value from our experimental data that was very similar to this, and we have the value from the Glowscript model. There were minor differences in the values, but that could account for, not having the magnometer lined up properly on our phones, or just various minor errors that can occur during the actual experimental process based on device changes from person to person. What if you had not originally oriented the experiment to account for magnetic north and instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? So the experimental data would become less accurate as Earth's magnetic field would be included in our measurements, making it much more difficult to find the same results that we did in our experimental setup this time. And what if the two sticks were identical and end to end, and then you run the same experiment again? How would you expect your measurements to differ? Measurements would increase by a factor of 2 if they are identical, and the direction would remain the same. That's all. Thank you for watching.